the cooling effectiveness, this is very easy. This is what you obtain for Tg minus Tm. Of course, these are average values, because we know Tg is not a constant, not as in the assumption that I have considered. I know also that Tm will not be a constant, and the minimum value that you can have of Tm will be Tk up, and so you see that you can define, in fact, the cooling efficiency like this. This is the maximum difference you could have, and this is the real one you have. So you see, if phi is equal to 100%, you would have this equal to that. That would be the largest cooling you could have. If phi is, let's say, high, that means that you have a high Tg for a rather low Tm. Okay? And you can find with the equations that I have written here, using the same result as the one that I have written here, you can find that Tg minus Tm divided by Tg minus Tk, it will be a function like this one. 1 plus Hg Lg divided by Hk Lk plus again Hg Lg divided by m dot k Cpk, and here I will have the height of the blade that is considered as the mean value. And you see that in fact these parameters that I have considered here are not really equal. We can understand their influence by physical explanations, but you need to go to equations in order to see that HgLg is present 2 times. So it's more important to fight against HgLg than to fight for HkLk, because HgLg is present 2 times, 1, 2, whereas this one is only present 1 time. And that's why most probably here you should represent this one higher than the C2. Film cooling is more changing the situation than the impingement cooling. But these are, let's say, not details, but things that we can discuss a priori. And you find back again the CPK that must be increased, and you find also the m dot k that should be increased, but you fight against that because globally it has a negative effect at the level of the engine. Okay? Of course, you do not find in this expression the influence of that. It's not here because it has been put in the efficiency, considering that Tk up is somewhere related with other parameters that we have here, and we see indeed that Tk up is not really a parameter. It's influenced by the pressure of the flow that you take at which place in the compressor, except if you have a heat exchanger. Except if you have a heat exchanger, then you are changing the situation. But otherwise, Tk up is somewhere fixed by the value of Hg. So because Hg is fixing the pressure you need inside the blade, and then it's fixing the pressure, so it's fixing the Tk up. Now, there is something else that we need also to discuss. First, I would like also to mention one point. Here, this is the technique that I have called film cooling. Film cooling. There is today in aircraft engines a technique that is an evolution of the film cooling. This is when you are using a porous material, that the blade is somewhere porous. So what do you have then? The blade is sweating air. The blade is cooled by what is called transpiration cooling. Transpiration cooling. And this is a technique that is even more efficient. More efficient than this, but I'm putting this together with the film cooling because it's a kind of extension. Okay? Now, something else that I've not discussed and that we should discuss, this is an effect that is hidden in what we have said without mentioning it. You see, I have discussed that an increase of the TIT is possible without cooling, but if you use cooling, you will have an effect due to the fact that the m dot in the turbine is lower, and the turbine efficiency is decreasing. But there is a second reason leading to a second decrease of the PIT. This is the fact that the isentropic efficiency of the turbine will decrease. Why? Why is it like this? You see, you have a blade of a turbine that is like this, and you are ejecting air through holes that you have here, holes that you have there. What are you doing at that moment? First, and maybe it's a small effect, but first you change the shape of the blade. So you have made everything so that the flow was following the blade. By injecting air, you are changing the external profile. And that means that the shape of the blade that you had optimized is now to be optimized with the presence of this buffer layer, this second layer, this intermediate layer of air. And the fact that you change the shape, it will lead to a decrease of the isentropic efficiency of the turbine. Maybe it's a rather small effect, but the second effect you will have is the fact that you have 2 times friction now. Indeed, you have a friction between the cold air and the blade, and a friction between the cold air and the hot air. It's like increasing by a factor 2 the size of the blade. And that will increase a lot the friction losses that you have in the turbine. Again, a reason, in fact, to decrease the isentropic efficiency of the turbine. So this is, so isentropic evolution, without cooling air, the flow would go into this direction, and you do not go there, you go in this direction, you see that you are increasing the friction. A third reason is the following. The air, even without film cooling, just by convection cooling, so even without film cooling, even without impingement cooling, just convection cooling, what do you have? The air that is flowing here is flowing centrifugally. It's leaving the blade, gaining and gaining R. So by moving into this direction, this air is increasing its work, its internal work, because it's moving from a small radius to a large radius. And so this air is escaping the blade with a higher work here than there. And so you are losing work because the escaping air is, let's say, taking with it a part of the work. So m dot k is containing a work that is leaving the blade and that will not be recuperated on the shaft of the turbine. And so you see that not only you are losing thrust due to the m dot k, but you are also losing thrust due to an isentropic efficiency of the turbine that is in fact lower than expected. And lower due to convection cooling, and even lower and lower when you are going to the film cooling. And this is an explanation why you are losing performance. But what you need to do is that you hope, as I've shown here, that this increase of the TIT, which is the gain, will be larger than this decrease plus this decrease. There are two losses of performance, or two origins of losses of performance in F and in TSFC, and there is one origin of increase of the performance, and you hope that the increase will be much larger than the sum of the two losses. Now, you see that I have really insisted on the m dot k, m dot k. Why do I insist on this m dot k? This is because the m dot k that we need to consider for cooling is really huge. It's really huge. So I'm representing that here. Let's imagine that you have one stator. So you have the combustion chamber. It's starting with a stator. So it's a stator that is attached to the external carter. So you have the external carter, and you have the stator 1 that we call very often the nozzle guide vanes. How much air do you need to cool down a stator like this one? Maybe you can say that it's 2%. 2% of what? 2% of m dot. That's why we will always write m dot k in function of m dot, in fact. Of course, if you speak about a turbofan, it will be a percentage of m dot primary. If you put a rotor here behind that is also cooled from the root, another 2%. Okay? But also you need to cool down the external side here. Maybe with some cooling air coming in this direction, some cooling air going there. So this external carter, again, you will take 2%. And also, you need to cool down the disc here. Again, here for the disc, you will use 2%. So you see that for one stage, 2, 4, 6, 8, 8% for one stage. If you have two stages that are cooled down, you see that you can use 16, 20% of your air. Easily, easily. And if you are not careful, if you are not using a decrease of that, an increase of that, in order to try to reduce m dot k, maybe the 16, 20% could become 20, 25, 30%. So can you imagine that 20 to 30% of the mass flow rate, or the primary mass flow rate, would not pass in the combustion chamber? That would be a huge effect at the level of the thrust.